Voyager 1 crossed the boundary of the solar system 5 times in 30 days. Not once, the way you've probably heard it. 5 times. Because the boundary itself was moving, oscillating back and forth while the spacecraft tried to pass through it. That detail didn't make many headlines in 2013 when it was published in Science. 3 separate papers, 3 independent instrument teams, 3 different anomalies, all confirmed, all in one issue. That's where this starts. The heliosphere is the bubble of charged particles and magnetic field that the sun blows outward into interstellar space. The heliopause is its outer edge, the point where the solar wind runs out of pressure and interstellar space begins. For decades, models described it as a relatively stable, roughly spherical boundary sitting at around 120 astronomical units from the sun. 1 astronomical unit is the distance from Earth to the sun. So we're talking about a boundary roughly 120 times that distance, about 18 billion kilometers. We sent 2 probes to find it. Voyager 1 launched September 5, 1977. Voyager 2 launched the same year on a different trajectory, aimed below the plane of the ecliptic. 2 separate angles of approach. The same destination. The signal from Voyager 1 takes 22.5 hours to reach us one way. Any command we send takes another 22.5 hours to arrive. The spacecraft runs on approximately 230 watts, the output of a single refrigerator light bulb. There are no spare parts, no repair ships. When it stops working, it stops working. The projected shutdown window is somewhere between 2025 and 2030. It is still transmitting. In August 2012, Voyager 1 detected a sharp drop in solar wind particles and a simultaneous spike in galactic cosmic rays. Those were the expected signatures of a heliopause crossing. What happened next wasn't expected at all. The transition occurred not once, but 5 times over a period of roughly 30 days. The particle counts would shift as if it had crossed the boundary, then shift back, then shift again. Kremagis et al., publishing in Science in June 2013, documented this directly. The only coherent interpretation was that the boundary itself was moving, surging outward and retreating, passing back and forth across the spacecraft's position. The models had described a fixed line. What Voyager 1 found was something that breathed. Before the actual crossing, the spacecraft entered a zone that had no name because it had not been predicted. Researchers called it the heliosynth depletion region, informally, the magnetic highway. Low-energy ions were streaming outward through it. Galactic cosmic rays were streaming inward, both simultaneously in opposite directions, through a region that was neither inside the solar system nor outside it. Stone et al., the second science paper from that same June 2013 issue, documented this in detail. The models had assumed a relatively clean transition, solar wind on one side, interstellar medium on the other. What actually existed between them was a third thing. A structure that had been invisible to every instrument that wasn't physically inside it. The question that comes to mind, and that nobody seems to have answered cleanly, is how many other predicted boundaries are actually regions? The magnetometer on board Voyager 1, designated MAG, is the instrument that caught most of these anomalies. It measures the direction and strength of the magnetic field continuously. The plasma wave system, PWS, detects electromagnetic oscillations in the surrounding plasma in the range of 0.2 to 0.4 kilohertz. Since 2017, it has been recording what researchers describe as a persistent low-level hum, a signal generated by the interstellar medium itself, dense enough to vibrate at measurable frequencies. Stella Acker et al. published that finding in Nature Astronomy in May 2021. There is a complication worth noting. The Plasma Science Instrument, PLS, which directly measures particle flux, stopped functioning on Voyager 1 in 1980. Everything the spacecraft has inferred about its plasma environment since then has been indirect, reconstructed from wave data rather than direct sampling. The plasma data everyone cites from Voyager 1 is technically a very sophisticated inference. Voyager 2 has a working PLS, which is one reason the November 2018 crossing matters so much. In late 2023, Voyager 1's Flight Data System, FDS, the onboard computer responsible for formatting and transmitting science data, began returning corrupted output, unreadable. By April 2024, engineers had identified the cause. Approximately 3% of the FDS memory had failed. The total memory capacity of that system is 69.63 kilobytes. Engineers developed a workaround, redistributing the affected code across undamaged memory addresses. The fix was uplinked. The acknowledgement received 45 hours later. A surgical procedure conducted across 25 billion kilometers, with no ability to observe the patient directly, and no fallback if it failed. It worked. When Voyager 1 finally crossed the heliopause in 2012, the MAG instrument recorded something that directly contradicted the prevailing theoretical models. The magnetic field on the outside of the boundary was aligned with the field on the inside. According to those models, crossing into interstellar space should have produced a field oriented toward what researchers call interstellar magnetic north, the expected direction of the galactic magnetic field in that region. Instead, the measured field deviated from that direction by more than 40 degrees. Berlage et al., the third paper from that June 2013 Science issue, documented this. It was not a measurement artifact. The magnetometer had been operating continuously since 1977, and its calibration history was well understood. A 2015 study from the University of New Hampshire offered an explanation. The IBEX mission. The Interstellar Boundary Explorer, a satellite observing the heliosphere from the inside, had identified a ribbon of energetic neutral atoms wrapping around the heliosphere's nose. The University of New Hampshire team proposed that this ribbon was deflecting the local interstellar magnetic field, bending it around the solar system the way a rubber band wraps around a ball. Voyager 1, moving through the distorted region behind that ribbon, would naturally measure a field that looked wrong compared to the far-field prediction. Their estimate was that the spacecraft would exit this disturbed zone around 2025. That date has passed. There has been no public confirmation either way. Probably there is a mundane continuation to that story that simply hasn't been published yet. Almost certainly. But consider the pattern of what gets announced and when. On November 5th, 2018, Voyager 2 crossed the heliopause. It was traveling below the ecliptic plane, a completely different direction from Voyager 1. It crossed at approximately 119 astronomical units from the Sun. Voyager 1 had crossed at 121.6 astronomical units. The difference, 2.6 astronomical units, roughly 390 million kilometers. Given that the two spacecraft approached from different angles, different hemispheres of the heliosphere, across a crossing 6 years apart, that similarity in distance was unexpected enough that multiple researchers noted it specifically. What the instruments found was a repetition. The magnetic field outside the boundary was again parallel to the field inside. The MAG data echoed Voyager 1's 2012 results almost structurally. And Voyager 2 also detected something Voyager 1 had not reported, a thin, hot layer of plasma sitting directly outside the heliopause, roughly 1 astronomical unit thick, described in subsequent analyses as a thermal pressure barrier. It had not been predicted by any pre-crossing model. 2 spacecraft, 2 directions, 6 years apart. The same anomalies. That is no longer a data point. That is a pattern. A 2024 study by Zernstein et al., published through Proceedings of the National Academy of Sciences, modeled how the heliopause position changes across the solar cycle. The conclusion: the boundary shifts by tens of astronomical units as the sun's activity waxes and wanes. It is not a fixed shell. It is a dynamic surface, expanding and contracting over decades in response to solar output. In the directions that Voyager 1 and 2 crossed, the boundary sits at 120 to 130 astronomical units from the sun. In polar and flank directions, it extends to 160 or even 180 astronomical units. The shape is not spherical. It is elongated, asymmetric, and in motion. Outside the boundary, particle density was measured at roughly 40 times higher than inside. And since 2020, Voyager data shows that interstellar plasma density continues increasing with distance from the sun, a trend that has not been explained. The interstellar medium, which prior models treated as a quiet and homogeneous background, is proving to be neither. The models described a boundary. What the data returned, across more than a decade of post-crossing measurements, is something that behaves more like a living interface. Turbulent, shifting, structured in ways the models didn't encode. Voyager 1 was designed for a 4-year mission. It launched in 1977. In November 2026, it will reach a distance of 1 light day from Earth. The first human-made object to cross that threshold, still transmitting, still sending data from a region we have never directly sampled with anything else, from a place where our models have already been wrong in at least 4 distinct and documented ways. The instruments are aging. The power is dropping. At some point in the next few years, the signal will stop. Everything we will ever know from direct measurement of that boundary, the anomalies, the patterns, the open questions about what the magnetic field was doing out there and why, will come from data these 2 spacecraft have already collected or will collect before they go silent. We built 2 probes in the 1970s, aimed them roughly outward, and they came back with a picture of the solar system's edge that doesn't match the one we had drawn. The boundary was not where the models placed it. The field pointed in the wrong direction. The region before the crossing had no name because no one had imagined it. And both spacecraft found the same anomalies from opposite sides. So here is the question worth sitting with. If the model was wrong about the boundary we'd been predicting for 50 years, which other edges, the ones we've only ever mapped from the inside, are waiting for something to pass through them?